Welcome back to the deep dive. Today, we are tackling a subject that sits right at the very edge of what we even consider intelligence.
Mm.
I mean, you look at modern AI, these, incredible systems like ChatGPT or Midjourney, and you see them do these amazing things. They write poetry, they recognize
They
faces.
could beat grandmasters at chess.
Exactly. And so the natural assumption is they must be smart, like actually genuinely smart.
And in a way they are. But
Yeah.
it's a very specific and slightly deceptive kind of smart.
How so?
It's the kind of smart that is absolutely fantastic at prediction, at guessing what comes next, but surprisingly terrible at understanding why something happened in the first place.
That is the perfect way to put it. It's the central paradox, isn't it? It's like a student who memorized every single answer key to every test ever, but if you change the question just a little bit,
They completely fall apart because they don't understand the subject.
yeah. And that brings us to the source material for today's deep dive. We are unpacking a pretty comprehensive survey. It's titled Causal Inference Meets Deep Learning.
It's by Liqing Zhao and a team from Zhejiang University, and it really gets to the heart of this problem.
So the mission for this deep dive is, well, pretty straightforward. We're going to explore how researchers are trying to give AI what we might call common sense.
Right. They're trying to take the pattern-finding superpower of deep learning and marry it with the logic-building power of something called causal inference.
Moving from machines that just see patterns to machines that can actually reason, that understand cause and effect.
That's the goal.
Okay, so let's unpack this. The paper starts with this huge problem, spurious correlations. I love that term.
It's a good one. In a data sense, it's kind of like a fake friendship. Deep learning, just relies on these massive amounts of data to find correlations.
It just sees that A usually happens with B.
Exactly. So it assumes they're linked. But a lot of the time, they're only linked by coincidence or by some background factor the AI can't even see.
And the paper gives this honestly terrifying example involving autonomous driving. This isn't just a glitch. This is life or death stuff.
Yeah, this is the classic robustness problem. So imagine you train a self-driving car model using data collected, let's say, entirely from roads in China,
Okay, so driving on the right side of the road.
driving on the right.
Mm.
The AI processes millions of hours of footage. It gets incredibly good at predicting that if it sees a car, that car should be on the right.
It learns the pattern.
Yeah.
It knows where cars go.
No, that's the thing. It learns the visual correlation. It learns that pixels of a car usually sit on pixels of the right lane, but it doesn't learn the rule.
Ah.
So then you take that same car and you drop it in the UK or Japan.
Where they drive on the left.
And
Oh,
boom,
boy.
catastrophic failure. Because the AI never learned the cause, drive on the side mandated by law. It just
Right.
memorized the pixels.
Yeah.
That is a spurious correlation in this new context.
Wow. That's a huge distinction. It's the difference between memorizing a map and actually understanding how to navigate. Right. If a road is closed and you've only memorized the map, you're stuck.
Precisely. And in high-stakes fields like healthcare or autonomous driving, we can't afford models that just guess based on pixels. We need them to be interpretable and trustworthy.
So if the goal is to make AI think more like us, I guess we need to start with how we think. The paper calls it brain-inspired reasoning.
It does. And this is where it gets really fascinating, bridging neuroscience and computer science. The paper talks about the dual process theory of the brain.
I think I've heard of this. Is this the whole System 1 versus System 2 thinking?
That's the one. System 1 is your intuitive reasoning. It's fast, it's automatic, emotional. It's based on experience.
Like catching a ball.
Exactly. You're not doing calculus in your head. You're just using System 1. And current deep learning is basically a super powerful System 1.
Yeah.
It's all intuition and pattern matching.
And System 2?
System 2 is logical reasoning. It's slow, controlled.
Yeah.
It handles causal logic. So if I ask you to solve a riddle or figure out why your coaster's broken, you switch to System 2. Causal inference is the attempt to build that System 2 into AI.
The paper uses this really specific, almost itchy analogy to explain it. The mosquito.
I love this one, the multi-sensory integration example. We've all
Yeah.
been there, right? You're sitting in a room, you hear buzzing sound auditory info,
Mhm.
you see a little black speck flying around visual info, and then bam, you feel an itch on your arm. That's tactile info.
My brain immediately screams, mosquito on my arm, swat it.
Right, that's System 1, bundling all that data together. But here's the twist. What if you feel the itch and you hear the buzz, but you clearly see the mosquito flying on the other side of the room?
Fox. I don't swat my arm. I figure the itch is something else.
Exactly. Your brain just performed causal inference. It reasoned The mosquito cannot be in two places at once. Therefore, the itch is not caused by the mosquito.
It overruled the correlation.
Yes. But a standard AI might struggle with that. It might just treat buzz, speck, and itch as one big data cluster and, swat the arm anyway, because those things usually go together in its training data.
It can't separate the signals. The paper mentions a specific part of the brain for this, doesn't it?
It does. The prefrontal cortex, the PFC. It handles working memory and attentional control. It's what filters out the confusion so you can focus.
So researchers are trying to build an artificial PFC.
In a sense, yeah. Giving the AI a way to filter out the itch when it knows the mosquito is somewhere else.
So we're trying to give the machine a prefrontal cortex. That's a tall order. To even start, you'd need a framework, a language for this logic.
Which brings us to what the paper calls the ladder of causality.
Okay.
This is a concept from Judea Pearl, who is basically the rock star of this field. Imagine a ladder with 3 rungs. Each rung is a higher level of intelligence.
Okay, I'm climbing. Rung number 1.
Rung 1 is association. This is just seeing. It's passive observation. The question is simply, if I see X, how likely is Y?
Like if I see clouds, how likely is rain?
Exactly. Or if a customer buys bread, how likely are they to buy butter? This is where pretty much all current AI lives. It's just fancy correlation.
Got it. Rung 2.
Rung 2 is intervention. This is doing. Now the question changes. It's, if I do X, will Y happen?
If I make it cloudy, will it rain? Which is a silly question, but I get the point.
It is, but it's the right kind of question.
Yeah.
Or, if I double the price of bread, will people still buy butter? This is active. And mathematically, this is where you introduce something called the do operator.
The do operator. Sounds like a dance move.
It's a mathematical tool, but it is so powerful. It's written as do t, and it's all about distinguishing between just seeing a variable change versus actively forcing it to change.
Why is that distinction so important?
Because observing reality is totally different from changing it. Think about a barometer, right? You observe the barometer drops, and then it rains. An association. But if you intervene, if you physically grab the needle and force it down, will that make it rain?
No. You've just broken your barometer.
Exactly. You performed a do operation, and the outcome was different. A pure correlation machine might think forcing the needle moves the weather. Causal inference knows it doesn't.
It's knowing that the rooster crowing doesn't cause the sun to rise.
Perfect example. The do operator lets us simulate these experiments without, breaking barometers.
So the top rung, level 3.
Level 3 is counterfactuals. This is imagining. The question here is, what would have happened if I had done X instead of Y?
What would have happened to my headache if I had taken aspirin instead of ibuprofen?
Right. And this is the highest level of intelligence because it requires you to imagine a world that never existed. You can't observe a counterfactual. You took the ibuprofen, that other timeline is gone.
You have to build a model of how the world works to even guess.
Exactly. And that's what we want AI to do, to ask, what would have happened to this patient if we gave them the other drug?
Wait, but real life is messy. There are all these other factors. The paper talks about a toolkit for blocking that noise. It mentions confounders.
Confounders are the arch nemesis of data science. Create the fake link between them.
Okay, give me an example.
Let's stick with medicine. You're testing a new drug. You see that people who take the drug have a lower recovery rate. So you might think, this drug is bad.
Seems logical. The data says drug equals sickness.
But what if age is a confounder? What if older people are more likely to be given the drug because they're sicker, and they're also less likely to recover just because they're older?
So age is influencing both things, who gets the drug and who gets better.
Precisely. It's skewing the results. So the toolkit gives us ways to fix this. The first is called backdoor adjustment.
Sounds like we're hacking the data.
In a way, you look at your causal map, you find that backdoor path through the confounder, through age, and you mathematically block it. You essentially compare old people who got the drug only to other old people who didn't.
You hold age constant.
You hold it constant to see the true relationship. And what if you can't see the confounder? What if it's some unknown genetic factor? Then you use front door adjustment. This is really clever. Instead of controlling for the unknown stuff, you find a mediator, a step between the cause and the effect that you can see.
Like what?
Like the dosage of the drug in the blood. You can measure that. If taking the pill causes the drug to appear in the blood, and the drug in the blood causes recovery, you can trace that front door path.
So you follow the chain of events.
You follow the chain of events. It's like detective work. You can't interview the witness, so you follow the footprints instead.
Okay, this is all making sense. We have the theory, the ladder, the tools. Now we have to talk about the elephant in the server room. Large language models. GPT-4, all of them. Do they actually think?
I mean, that is the debate, isn't it? The paper brings up the parrot problem. LLMs are trained on just massive amounts of text. They get really good at knowing which words follow other words.
But do they know cause and effect, or are they just really convincing parrots?
Exactly. And the paper has this hilarious failure case that shows the problem, the walking on a bed example.
I saw that. They asked an LLM, what happens if a person walks on a bed instead of the street?
Mm-hmm. And the answer?
The LLM said, they would be late.
They would be late.
Not they'd fall off or it would be weird. Late? Why?
Because the model saw the linguistic pattern walking on X instead of the street.
Yeah.
And it just associated that with commuting scenarios from its training data.
So it thought of traffic. It didn't think about physics.
It missed the physical reality that a bed is a piece of furniture. It just relied on word association rung one of the ladder, not true reasoning.
So they're just dumb parrots.
Well, not entirely. The paper does note they're actually pretty useful for something called causal discovery.
How?
They've read the internet, they have a lot of background knowledge, they know rain causes wet ground, not the other way around. So you can give them a data set with variables, and they can look at the names and propose a first draft of a causal graph.
So they're like a research assistant, they sketch out the hypothesis, and a human comes in to verify it.
That's a great way to put it. They're good at proposing ideas, even if they sometimes think you can commute on a mattress.
Okay, let's get into some real-world applications. We talked about driving, but the paper highlights some other fascinating areas like computer vision, medical imaging.
Oh, this is a huge area. Doctors use AI to segment cells, basically to outline the nucleus of a cell in a picture to look for cancer.
And standard AI gets confused by blurry images.
By blurry images, by noise, yeah.
Yeah.
It doesn't know where the edge really is. But the paper mentions a causal method, SAM, that can distinguish the true cell boundary from noise. It asks, is this pixel dark because it's the cell or because of a shadow?
It separates the signal from the noise. That leads right into visual question answering, or VQA.
Right, where you show an AI a picture and ask a question. And VQA models are notoriously lazy. They have this visual common sense bias.
Meaning what?
Meaning if the AI sees a dining table, it just assumes there must be chairs nearby, because in its training data, tables and chairs almost always appear together.
So if I show it a picture of a table in an empty room and ask, are there chairs, it might just say yes.
It might. Causal inference helps the model separate the object, the table, from the context, the room. So it can answer accurately, even if the scene is weird, like a table in a garage.
Yeah.
It breaks that spurious correlation.
That seems vital for something like a search and rescue drone. You don't want it ignoring a person because people aren't usually on rooftops.
Exactly. That's an out-of-distribution scenario. And that's where causal models are supposed to shine.
Okay, one last application that hits close to home for all of us. Recommendation system.
Ah, yes. Netflix, Amazon. We've all gotten a recommendation that makes absolutely no sense.
Or you get stuck in a feedback loop. You click on one cat video and suddenly that's all you see.
The paper talks about something called counterfactual explainable recommendation, or counter.
Clever.
Very. So instead of just saying, buy this because you bought that, the system uses counterfactuals. It can tell you, if you hadn't bought the hiking boots, we wouldn't have recommended the tent.
Oh, that creates transparency. It tells me exactly what action led to the suggestion.
Exactly.
Yeah.
And it also lets the engineers test for fairness. They can run a counterfactual like, if this user had the exact same watch history, but a different zip code, would the recommendation change?
And if the answer is yes, then you know there's a bias in the data. The zip code is driving the recommendation, which it shouldn't be.
You got it.
Yeah.
It helps build systems that are more logically consistent and hopefully more fair.
So wrapping this all up, where are we? It feels like we are on the edge of a pretty big shift.
I think we are. We're moving from an era of purely data-driven AI to causal-driven AI. For the last 10 years, the strategy was always just add more data.
Right. If the model failed, feed it a trillion more words. But you can't brute force common sense.
You can't. And this is all connected to the quest for strong AI. You know, machines that don't just calculate, but truly think. Machines that can handle those out-of-distribution scenarios, like driving in a new country without needing to see a million examples first.
But the paper does end on a note of caution. This is not a solved problem.
Oh, far from it. The biggest hurdle is that we lack benchmark data sets for counterfactuals. I mean, think about it. You can't observe what didn't happen in the real world. We don't have a data set of, what if I took the train? Because, well, you drove.
That's a mind-bending problem. How do you test a model on things that never happened?
That's the frontier of the science right now. It's not easy.
So as we wrap up, I want to leave our listeners with a final thought. We've been judging AI on its ability to climb this ladder of causality, but I'm wondering, where are we on that ladder?
That is the provocative question, isn't it? We all like to think we're at level 3, masters of counterfactuals. But how often do we just operate at level 1?
Just reacting to associations.
Exactly. I ate this, then I felt bad, therefore the food was bad. That's pure association. Did you consider the counterfactuals? Would I have felt bad anyway because I was stressed?
So the challenge for you, the listener, is this. Are you analyzing the why, the counterfactuals, or are you just reacting to the what, the correlations?
In a world of information overload, climbing that ladder is hard work. But it's really the only way to get to the truth.
And on that thought, we will let you get back to your own causal inferences. Thanks for listening to The Deep Dive.
We'll catch you next time.